Hi everyone, this is Nick Jacobs, your math instructor here at Yavapai College for Intermediate Algebra. Today we're going to begin Chapter 7, Rational Expressions. So I'm just going to be giving an introduction. And this will be a pretty short lecture compared to some of the past ones. So let's get started. Today we're going to be evaluating rational expressions, simplifying rational expressions, and then solving applications with them. Actually, you know what? I think I took out solving applications. So for this section, there won't be any sort of word problems or application problems. We'll kind of just evaluate and simplify them. But before we get into that, let's just kind of define what a rational expression is. So rational expressions are expressions that can be written as quotients, so fractions of two polynomials. So there's kind of a couple of different things with that, but examples of rational expressions would be maybe 5 over x. So 5 is a polynomial, x is a polynomial, x squared over 3x minus 4. Again, both polynomials, and then this last one. So a rational expression, again, it can be written as a fraction or as a quotient. The numerator and the denominator need to be polynomials. And then the other rule is that the denominator cannot be 0. So you cannot have 0 in your denominator. 0 could be in the numerator, cannot be in the denominator. And you guys will have a simple homework question on that too, where it'll ask you what are the properties of rational expressions. You just need two polynomials and the denominator cannot be 0. And we'll actually talk a little bit more about that, that fact as well here when we get into some examples. But for now, we're going to be doing some of these. So if possible, evaluate each expression for the given value of the variable. So these are all rational expressions. And what we're doing is we are taking the they give you a specific value for the variable, and we're just going to substitute that into the rational expression to get a simplified answer or to evaluate these. So our rational expression here in A is 1 over x plus 3. And they want to know what is the value of this when x is equal to 3. So all we have to do is we just plug in 3 where we see the x. And we simplify. So we'd have 1 over 6. Okay, the next one, the next rational expression is w squared all over 3w minus 4. And they want to know, again, the value of that when w is equal to 4. So we just simply plug in 4 wherever we see a w above. So we have 4 squared. And I usually use a parentheses. That helps if I have a negative, right? We know that when we would have maybe a negative 4 squared, it matters if you have parentheses or not around it, right? So if this was w equals negative 4, we're definitely going to want to have parentheses around it, because if we don't, your calculator would give you a negative 16 instead of positive 16. And we know 2 negatives multiply to be a positive. So let's just keep going with this problem. So we continue to plug in the 4. Sometimes I get off on tangents there. I apologize for that. But 4 squared on the numerator is 16. And then in the denominator, we have 3 times 4, which is 12. And 12 minus 4 is going to give us 8. And we know 16 divided by 8 is equal to 2. All right, and then the last one, we want to find the value for this rational expression where w minus 4, what is the value when it's all over w minus 4? So, 4 minus w over w minus 4. So when w equals negative 5, and the only little thing here to be aware of is this negative 5 when we substitute for w. So some people make a mistake with this step is they'll just say this is minus 5, but we have to have that negative in there. And again, that's why it helps to have parentheses. For some of these, you can even do it over here when it's starting out as a variable. So w is negative 5 minus 4. So 4 minus a negative 5 is going to end up being 4 plus 5, right? A minus gives us a plus plus. Change both of those signs. And then this is -5 minus 4. So a -5 minus a 4, which is a -9. So 4 plus 5 is 9. 9 divided by -9 is going to give us a -1. And that's the value of that expression. So just a few quick examples there of when they ask you to evaluate given a specific value for a variable. Some people, let me just make one more comment. Some people will try to like solve for X or something like that, and they'll kind of miss this whole fact here that they give you a variable value. Okay, we're not solving for a variable, we're substituting and simplifying. And these next ones, and this goes back to the fact that the denominator cannot equal 0 in a rational expression. So they want us to find all the values of the variable for which each expression is undefined. Okay, so we just learned that you cannot define a rational expression when the denominator is equal to 0. So basically, we need to find what values make the denominator 0. Well, of course, in this one, 1 over x squared, if you substitute 0 in for x squared, 0 squared is going to equal to 0, or is going to be equal to 0. So we know that 0 does not work in this case. And if you want to kind of figure that out mathematically, what we do is we take the denominator. So we take this guy, okay, and I'll just move it down here. And we take the denominator and we set it equal to 0, because that's going to tell me what values make that denominator equal to 0, right? And in something like this, if we're actually solving this, we're going to square root both sides. So we're going to square root x squared, right? And we're going to square root 0. The square root of x squared we know is x, and the square root of 0 is 0. So when x equals 0, this rational expression is undefined, because when we substitute 0 back in here, we're going to get a 0 in the denominator. Now, the next one, you can probably tell without using this method that a value of 4 for w is going to make the denominator 0. And that's exactly what your answer is going to be. Okay, we know that this rational expression is going to be undefined when w is equal to 4. Okay, now again, if you want kind of a method to do that, you would just take your denominator, so take this guy and set it equal to 0. Okay, don't even have to worry about the numerator in these. Okay, just look at the denominator and solve it like it was an equation. So when w equals 4, that's when the denominator is going to be 0. It doesn't matter that when we would substitute 4 in for the numerator, it would be 16. Doesn't matter at all, right? So if we did that, if we plug 4 back in here, okay, we would end up with 16 over 0. Well, we know that we can't divide by 0, so this is going to be undefined. All right, and then the last one, 6 over w squared minus 4. Okay, you may notice that if we have a 2 in here, 2 squared is 4. So 4 minus 4 is going to be 0. That's going to make this undefined. But there's also another value that works, right? When we have a w squared, what's the other value? Okay, it's a -2, because -2 squared, or -2 times -2, is equal to +4. And 4 minus 4 gives a value of 0 in that denominator. Again, if you don't recognize that, take your denominator and set it equal to 0, and then solve. So we have w squared equals 4, and then we square root, right? And this is where you have to kind of go back to the last chapters and to know that when we square root this, we also have a positive or a negative value. So the square root of 4 is plus or minus 2. So when is this rational expression undefined? When w is equal to +2 or -2. And your homework might have like a comma separated list or something like that. So you can kind of write it like this, just 2, -2, or you could just flip it around, -2, 2. All right, this next part is we're going to get into simplifying rational expressions a little bit more. So we're not, we're not plugging in a value. We're not finding where the denominator is going to be equal to 0. We're just simplifying. And the way that I'm going to start this off is I'm going to have some examples. We're going to go back to when we simplified fractions. Okay, so we're going to be applying the basic principle of simplifying fractions to be able to then apply that to simplifying rational expressions. So remember when we simplified fractions, this is way back in, we didn't do this really in this class, but way back in maybe middle school or possibly before that, we found the greatest common factor, right? And we did find the greatest common factor earlier this semester in chapter 6 when we were factoring, but we know that the greatest common factor of 9 and 15 is 3, right? The greatest common factor of 9 and 15 is 3. How do I know that? Well, if you wrote out multiples of each of these, we would know that 3 times 3 is 9. We know that 3 times 15, or sorry, 3 times 5 is 15. And this is what they have in common, just one of the 3s. So that's your greatest common factor. And then, whoops, let me go on a little bit here. So then what we do to simplify this is we take the GCF and we're actually going to, well, there's a couple different ways that we could do it. We could divide it by 3, okay? Or we could kind of break this up. So we could go, right, divide by 3, divided by 3. That's going to give us 3/5. Okay, and you can kind of see that up here, 3/5. Or what you could do is you could take 9 and you could make it into that 3 times 3. 15 is 3 times 5, and then cross off that common factor. Okay. This is typically the way that I'm going to do it here when I'm simplifying rational expressions. So I'll do the next one like that as well. So let's find the GCF of 20 and 28. Well, what's the GCF of those? Well, we know that 20 is the same thing as 2 times 2 times 5. 28 is 2 times 2 times 7. And these have a 2 and another 2 in common. So 2 times 2 is 4. That's the greatest common factor. And when we're simplifying it, we kind of do the same thing that I wrote above. Okay, we could divide top and bottom by 4. That would give you your answer. Or you can kind of split it up like this. Actually, I'm not going to write a 2 there. I just found the GCF to be 4. So what I'm going to write is 4 times 5 is the same thing as 20. And then 4 times 7 is the same thing as 28. And then I can cancel that greatest common factor out of those two, and I'm left with 5/7. Again, you could take 20 divided by 4, and that's 5. And then 28 divided by 4 is 7. However you want to do it. I don't really care. Now the GCF of 45 and 135. So you might have to do a little bit of work here. I know 45 is equal to 3 times 3 times 5. I got that from 9 times 5. 135 is equal to 3 times 3 times 5 times another 3, actually. So the greatest common factor in these is actually going to be 45. You can kind of double check that this all multiplies to 135. But what you can do in this one is you can say 45 is the same thing as 45 times 1. 135 is the same thing as 45 times 3. And then you can just cancel these 45s out and you're just left with 1/3. If we were simplifying that fraction. So you're not going to have any homework problems on things like this, but this is going to get us into our basic principle of simplifying rational expressions. So our following property can be used to simplify rational expressions where P, Q, and R are polynomials. So if I have a rational expression and I factor out a common factor, or I write it as, factors multiplied by each other, I can cancel a common factor. Okay, that's kind of what we just did. And so I could cancel out R in this case and to be left with P over Q. All right, and the one thing that we also need again is that the denominator cannot be 0. So P or R cannot be 0 because if I multiply anything times 0, that's going to give us 0 in the, and that doesn't work here in our denominator. So let's simplify some rational expressions now. So these are the ones that have variables. Again, we are not solving for y or x or whatever the variable is. We are just simplifying or crossing out common factors. So I have 16y over 4y squared. I'm going to rewrite that down here. I think I'm going to have just a little bit more space. And then I'm going to write it out using factors. So 16 is the same thing as 2 times 2 times 2 times 2. And then I have the y at the end there. Okay. 4y squared is the same thing as 2 times 2 times y times y. And then what I do here, and I'll use a different color if that helps you, I'm going to cancel out common factors. And I'm left with, in this case, 2 times 2 on the top, and then just the y in the bottom. So I'm left with 2 times 2 over y, which is 4 over y, and that's simplified. Okay, so again, you could find the GCF. You could recognize that that's 4y. Those both have a 4 and a y, and you could divide it. Okay, that's the other method. And then you would still get your same answer there. I just think this is a little bit easier when we're kind of writing it out, but we will maybe get to the point where we have things, that it just doesn't make sense to write all of it out like this. Okay, you could have also recognized in this case that your GCF of 16 and 4 is 4. So you could have written it out as 4 times y, and then the other one is 4 times y times y, and you or sorry, yeah, 16, sorry, on the top should be 4 times y. So then the 4's would have canceled, one of the y's would have canceled, and you still would have had 4 over y. The next one is 3x plus 12 over 4x plus 16. So you'll recognize this, maybe the 3x plus 12, that we can take out a 3 from those, right? Going back to kind of chapter 6 here, okay? So recognize that you could factor out a 3. So let me rewrite this. So on the top, I can factor out a 3, and then I have x plus 4 left over. And on the bottom, I can factor out a 4, and I have x plus 4 again. And then we recognize that the x plus 4s are the same thing. So I can cancel out that common factor, and I'm simply left with 3/4 in this case. So I'm just simplifying. Now the next one, let's factor the top. So we recognize this is a difference of 2 squares. Wow, that's going all the way back to chapter 6, right? So this is a difference of squares. And x squared minus 25, remember that factors into x plus 5 times x minus 5. Okay, and then this guy, this is a trinomial. Okay, it's not a perfect square trinomial because 2 is not a perfect square. 15 is not a perfect square either. But we need to be able to factor this. So remember what we did back in chapter 6 is we took 2 times negative 15. And we got negative 30, and we were splitting the middle term. So we said that I need factors of 30, of negative 30 that add to negative 7, and that would be negative 10 and 3. So we split this middle term into 2x squared minus a 10x plus a 3x. So those two give us the negative 7x, then minus the 15. And then we factored this, right? So we took out a 2x here because that's the GCF of these two, right? We factored by grouping, and we got an x minus a 5. And then here we took out a 3 from the 3x and the minus 15. And we got an x minus 5. And so this all factors, let me write this down here, into 2x plus 3 times x minus 5. Okay, and that's what you're working with here to be able to cancel a common factor. And we see we can cancel the x minus 5s in this case. And so your final answer is x plus 5 over 2x plus 3. Get some water. All right, so again, you're looking to see if you can factor the numerator. Do that first. See if you can factor the denominator, factor that out, and then cancel any common factors. That's basically the process of simplifying rational expressions. Let's just do a couple more examples, and then that'll be it for this chapter. So I have a negative y minus 7 over 2y plus 14. Okay, well, let's kind of look at this. We're trying to factor out a common factor. I don't like that this one starts with a negative. Okay, so in the numerator, let's try to take out, and this is kind of a little trick, you can take out a -1. And you can always do that. I could take out a -1 here. It would just, change the signs of these. So this changes to a positive y plus a 7. So I factored out a -1. It just changed the signs of these two guys. Okay. Now what can you factor out of here? 2y plus 14. Well, I know that I can factor out a 2. And that leaves me with a y plus 7. And look at that. Now we have two common factors. We can cancel those out, and I'm left with a -1/2. So that starting rational expression after all that just simplified to -1/2. Now this guy, some people, get these a little bit confused, and they'll say, oh, I have 8 minus x and x minus 8. Definitely not the same thing, okay? These signs are switched, right? This is a positive 8. This is a -8. This is a -x. This is a positive x. The only thing here is that I have this minus sign out front. Let's see what that does. And what I can basically do with that minus sign is I can distribute it to the numerator. Or I can write it like this. I can say it's a minus and then an 8 minus x in parentheses. Okay, so I move the negative to the top, which means I need to distribute it to the entire numerator. Okay, you wouldn't really distribute it to the denominator. You could, but it's very much more typical to distribute to the numerator. So then when I distribute it, it's just going to change the signs here. It's going to be a -8 and a positive x. And I know that -8 plus x is the same thing as x minus 8. So I can just flip those around, and now look at that. I have 2x minus 8s. Now you can cancel those, okay? The thing is your answer is not 0. When you cancel those, it's a 1. Why is it a 1? Because I could have factored out a 1 in this step right here, okay? So then when I cancel those two, I'm left with 1 over 1, which is just 1. Let me show you another example. This comes up a lot. Let's say this problem was 8 minus x over x minus 8. Okay, I don't have the negative out front. All right. So what I'm going to do with this is I'm going to flip this around. I'm going to say this is -x plus 8. And I'm going to leave the bottom as x minus 8. Now, I still want to try to factor out a common factor. So what do? I kind of do the same trick that I did in part A here. I'm going to factor a -1 out of the numerator. So take a -1 out. That's going to change this to x minus 8. And look at that. I have an x minus 8 in the denominator. If it helps you to put parentheses around this, you can. You can still cancel out those common factors. It doesn't have to be in parentheses. Okay, and look what I'm left with here. I'm just left with this -1. Okay, or really -1 over 1. You can always have it over 1. Okay, you can always factor a 1 out, but this is just a -1. So notice the difference in these. Essentially the same problem, just this negative out front makes it a little bit trickier sometimes. You're going to end up with a +1 here, a -1 in this case. So Guys, that is it for 7.1. We will see you next in 7.2. And again, we have several sections to go through. Hopefully the lectures in this chapter are a little bit shorter than they've been. So we'll see you next time.